Now we want to talk a little different concept about applying stoichiometry to when we do reactions with solutions, like we talked about earlier in this chapter. So the whole purpose of stoichiometry is that we're dealing with reactant and product amounts, right? You need this much product, you'll get that much reactant, that kind of stuff. And so when all the relationships are based around moles. So for example, Al2O3 becomes 4Al plus 3O2. That relationship really is in the moles. So 1 mole of Al2O3 will give you 2 moles of aluminum. Okay, and so that gives you that relationship. But the thing is, we need the molar mass to represent those mole amounts as a useful measurement, namely mass, right? Because really, if you're going to be selling aluminum, well, like say that's you're actually selling aluminum foil, you'd want to know how much mass you have, because the price is going to be per mass, not per mole. Conversely, when you dig a rock out of the ground, you put it on a balance to see how much it weighs, then you can do these conversions into moles using molar mass. Could look at a similar but slightly different reaction. Say copper 2 chloride plus zinc becomes copper and zinc chloride. And so stoichiometry tells me that's going to be a mole relationship. If I have 2 moles of the copper 2 chloride, that would react and become 2 moles of copper solid, right? Because the relationship is all about the moles. So say target amount is this 2 moles of copper. If I want to turn that into a useful amount, it'd be mass. I can use molar mass. And because it's a solid, that's a meaningful quantity. If I instead look at, say, copper 2 chloride, in this reaction, it's dissolved in solution. It's aqueous. So I need 2 moles of copper 2 chloride, but now that is the solute, the amount of solute that's floating around in this solution. But because it's a reactant, if I'm going to go get the solution and measure out an amount of it, I'd want a volume of that solution, right? I want a volume of the solution, a volume of liquid that I can measure out, say in a graduated cylinder, that I could then pour into my reaction mixture. I do need a target amount of moles of solute, but if I got a mass of copper 2 chloride, that's not a useful measurement. The whole point of using molar mass and converting into grams is to get a more useful measurement that I can then use, like measure out in a balance. So I want volume for solutions. That means I'm going to need a conversion factor that relates moles of solute to liters of solution. And that's molarity. So molarity is the relationship of moles of solute per liter of solution. So that's what we are going to have to use here in order to do this relationship. So molarity is going to function similarly to the molar mass in doing stoichiometry, that it allows you to convert between the mole perspective or mole description that's actually useful from a stoichiometry point of view, and the liters or volume measurement that is actually useful in the laboratory setting. So consider the following reaction. I have copper 2 chloride plus zinc becomes copper plus zinc chloride. If an excess of zinc solid is used, what volume of a 0.60 molar copper 2 chloride aqueous solution must be used to yield 0.95 grams of copper solid? All right, what do we want? I am explicitly after a volume of solution. So I want a volume of solution of this reactant copper 2 chloride. So what do I have? What can I relate it to? I know I'm given a reaction, so I am likely doing a stoichiometry problem. So I want to relate it to an amount of, say, another reactant or of a product, what I'm looking for. And so I can see I have 0.95 grams of copper solid. That is a reactant product, in this reaction that I'm really looking for. That's what I'm based off of. I'm given this amount of copper product that I want, and I'm going to be doing some stoichiometry to relate it to the copper 2 chloride. The other piece of information that I have is the 0.6 molar CuCl2. Now, we may be tempted to see that amount, that 0.6 molar CuCl2, and try to use that as our starting point. But one of the things that we can see is we're after a volume, which is an amount of stuff. So we're going to need to do a conversion from something that is also an amount of stuff. Mass is a different type of measurement, how much, not how much space like volume measures, but that's still a sign that this is the actual conversion that I'm going to be doing. When I'm given a molarity like I have here, that's a ratio. That is an amount of stuff per volume that is likely to be used as a conversion factor. It is a conversion factor that lets me go between moles and volume of the moles of solute in a volume of the solution that I'm talking about. So that's going to be a conversion factor. It's something we're going to use. You'll note it has to be defined, unlike molar mass that you can be expected to either calculate it or they'll be given it to look up. But the molarity is something that always has to be given for every problem. That would be unique for the solution you're talking about. Also, do want to point out that there is this fact that you're told that zinc is in excess. So this has kind of been mentioned in previous problems, maybe. I haven't really brought it up, but now that we know what a limiting reagent is, if zinc is in excess, that is one of my reactants, that means the other reactant, copper 2 chloride, has to be the limiting reagent. So what that means is you'll note we are asked about the yield of copper. So that's the theoretical yield that I'm after. Because copper 2 chloride is the limiting reagent, that's what we want to do stoichiometry off of to determine my theoretical yield. So we have a little more context. There's information kind of cooked into this problem that we can kind of passively use to guide how we would do this stoichiometry. It's just kind of there as important kind of context. Okay, so we want to know what volume of this solution that we're dealing with. And so we have two values, and it really can be kind of difficult. A lot of times stoichiometry, we just have one starting value and the rest for an ending value. When we have two values that we're starting with, how we can pick which one is kind of where we want to start what we're dealing with is that volume is an absolute amount. It's a volume, it's an amount of solution, an amount of liquid. Mass is also an amount of stuff. It's just a different type of measurement, whereas this is a concentration. That is a ratio, and we see that capital M, that means molarity. That is a ratio. That means it's likely going to be used as a unit conversion as opposed to just a straight up amount. So these quantities right here, volume and the 0.95 grams, are more similar to each other. And so they are what are going to be our start and our end point. So we can see it's different substances, copper and copper 2 chloride. So that means we're going to need to do some stoichiometry to get that. And the relationship is going to be based on the balanced reaction coefficients. So I have 0.95 grams of copper. And I know that the first thing I always want to do is get that out of mass into moles. And so I'm going to need the molar mass of copper to do that. And I know that that is 63.55 grams per mole. Okay, and I know that my molar mass here would be 63.55 grams per mole, right? That is the molar mass that I'm working with. And so when I do this, I'm taking my grams, dividing it by that, and that gives me the number of moles of copper that I'm working with. Now that I'm into moles, I can use those reaction coefficients, and I know that I want to go from moles of copper to moles of copper 2 chloride. And I can use those coefficients. This is a balanced reaction. It's just 1 and 1. So for every 1 mole of copper, I would expect that I may need 1 mole of copper 2 chloride. And so now that I have an amount of copper 2 chloride, I know that in this reaction, this would give me the moles of copper 2 chloride. Previously, we have used molar mass to then get a mass of copper 2 chloride, which would be useful. And we want to do something similar, but instead of moles, I want a volume because it's a solution. We talk about liquids, like aqueous solutions, in terms of volume, And that's where our molarity comes in. So when I have 0.60 molar of the copper 2 chloride, what that tells me is that I have 0.60 moles of the copper 2 chloride per 1 liter of solution. That's the definition of molarity that we have previously seen. And so we can use this as a ratio, 0.60 moles per 1 liter of solution. And then we use this as the molarity of the solution that I have right there. And so my grams cancels out, my grams of copper, my moles of copper, my moles of the copper 2 chloride. I'm left with liters of solution. If I multiply it all out, multiply across the top, divide, multiply across the top, divide, multiply across the top, divide, I get 0.025 liters. And so that is the volume that I would want to use. 2 sig figs comes from the 0.95. So that would be the appropriate volume that I would use. You'll note the 0.025 is a little small in terms of liters. More commonly, we would say 0.025 liters. We know that in 1 liter, I have 1,000 milliliters, and this becomes 25 milliliters. That's not mandatory, 0.025 liters, totally acceptable response. Just in terms of usefulness and utility, milliliters is more common. We saw that previously when we defined molarity, that a lot of time molarity is always per liter. That's part of the definition. But a lot of times when we're working with actual volumes, we use milliliters in the lab because that's just a more reasonable amount of volume. Liter scale chemistry is that's a lot of solution to be using for your reaction. But in this case, we have gotten a useful amount. The whole point of stoichiometry is to take an amount, right? I want to make a target amount of product. So I want 0.95 grams of this product. So I'm going to need to start with 25 milliliters of this reactant, right? And that is what the purpose of stoichiometry is. It gives me useful answers to relate amounts. And when we're dealing with solutions, we want that to be a volume. That is it for chapter 4. It was a long one. You want to be able, we've gotten into this, I'm blanking all this stoichiometry stuff, and we want to be able to do stoichiometry, but we want to not forget that, we learned just setting up chemical equations, phases, balancing equations, all these ideas from the fundamentals of chemical equations. Those ideas will all still be covered when we go to assess these things, when we take our participation quizzes, when we do our the exams, all that stuff, all looking at the type patterns of reactions, combustion, solubility, net ionics, acid-base reactions. Right? There's a lot here. We've been doing chapter 4 for a while. We're finally done, but we do want to not get. It's not only going to be stoichiometry when we're looking at doing when I'm looking at asking questions on quizzes and tests about chapter 4. Everything about reactions and stoichiometry, all going to be on there. So 4 questions on 615. You want to get all of them answered. You want to answer all of them, get all of them answered, get those answers submitted over on Blackboard by Monday night. And then we'll have the Tuesday participation, which will start in on chapter 5. Tomorrow on the Tuesday at 9 a.m. we'll do a chapter 4 participation quiz. It will only cover topics in the participation questions from chapter 4. That was 3 assignments, everything from module 4, and then this one, 615. So there's a decent number of questions, decent number of potential topics, but get some review with that. We will do, after the participation quiz, we'll go to the lab and do reactivity patterns, but make sure you take care of the pre-lab stuff before that. And then we'll have exam 2 on Thursday, covering all of chapter 4 and then the bit of chapter 5 that's on the 616 participation assignment. And then heat effects lab, lecture module 6. And as a note, no Friday participation this week. As Juneteenth holiday, City of Baytown is programming. I encourage you to check it out, or just enjoy stuff outside. But if you have any questions, let me know. Oh, there will be the answers for the participation that go live Monday night. Otherwise, that is it for me. That's it for chapter 4. All this stuff. Otherwise, I'll see you hopefully on campus tomorrow on another video this week. Who knows? See you around. Bye bye.